Hi, welcome to Ionic Bonding and Physical Properties. So please answer these questions before continuing on. And let's go. So, what are ionic compounds? So they're one of the two types of compounds we'll be looking at. Ionic compounds have positive and negative ions, not atoms but ions. And they're an equal number to where the positive and negative charges cancel out. That doesn't mean you have equal number of cations and anions, but that means the charges will be equal. So an ionic compound itself is neutrally charged. They make these big structures, these lattices that you see over here. And these lattices are these bigger structures, so they're never isolated by themselves. Sodium chloride builds this lattice with 6 chlorine around each sodium and 6 sodiums around each chlorine. They are never isolated by themselves. Cesium chloride actually has 8 chlorides around each of these. They come in different sizes and different crystal shapes, which we'll see a little bit later. These very crystals are the main evidence for the physical properties that ionic compounds demonstrate. Now, quite often we think an ionic compound occurs by an electron being given up to the anion. That's not always the case, as we'll see in a little bit. But this is quite often what you'll see in textbooks, but it's not really 100% the truth. So let's take a look at what that truth really is. Now, what you saw in the previous is a little more simplified here, just looking at the valence electrons. Currently, before the electron is given up, this is a sodium atom and a chlorine atom. Sodium and chlorine are super reactive in any natural environment. They're not likely to be found as atoms. So the fact of this occurring would be extremely rare and under mostly man-made circumstances. So this one isn't really how ionic bonding occurs. However, what is much more the case is when you have ions floating around in solution. So these are dissolved solids. When they're in water, ionic compounds often dissolve. And so the individual ions are free to roam about. And essentially the water gets in the way of them recombining. That's why they remain what are called in solution, separate. Same holds true in each of these two solutions. When we mix the solution together, though, what ends up happening is the potassium and iodide forms this crystal lattice, nice structure here, all throughout, and that crystal lattice makes a solid. This solid does not dissolve in water. So an ionic compound has formed. This one doesn't dissolve in water, so that's why it remains a crystalline solid. This is the most common. Ions attract, and a new compound forms. This can even happen in your body if you've ever heard of kidney stones. That's calcium from your blood, carbonate that gets built up in your kidneys. They combine to form calcium carbonate, which is very insoluble in water, which we mostly are. Therefore, the stone builds and builds and builds until, ouch, no bueno. Now, another way they can happen is if we have the things dissolved in. As we look back at the previous, you have the potassium and the nitrate. So if you got rid of all of the precipitate, you removed it, filtered it out or something, you'd be left with the ions in solution. Now think of the water is really getting in the way of the two ions forming back together. However, if you get rid of the water, right, you boil it off, it evaporates, and so on. Now the positive ion attracts the negative ion, you get ionic bonding, you get crystals formed. You can take this with salt water, boil off all the water, you'll be left with salt again. You're having the dissolved ions reform into the crystalline compound solid. This happens quite a bit in a variety of ways. So the last two are more common. Essentially the first one most, second one, second most common. Well, starting off with atoms, not very likely. Now another important set of ions that have been mentioned so far are polyatomic ions. These are covalently bonded in a resulting of an ion. So they usually start off with elements, like in this case phosphate, all nonmetals that will share electrons. We'll talk more about what covalent compounds really are, but the result, they're only able to do this because they have 3 extra electrons. And so because they have 3 extra electrons, they're able to form this stable ion, which can then bond ionically to other things. So in a polyatomic ion, when it is bonded in an ionic compound, it has ionic bonds keeping it in place, and what keeps the polyatomic ion together are covalent bonds. Covalent bonds keep polyatomic ions together. Ionic bonds keep ionic compounds together. There's a list right here. I think it's the same list you have on your reference sheet. There's many more. We'll stick to this one because it's got a wide variety of things we do use, some things we don't, but it get your feet wet with this. All right, here are some physical properties of ionic compounds. You can read through those pretty well. So let's explain the why, because chemistry is not about just identifying, but it's about describing, giving reasoning, and explaining why these things occur so we can use those concepts in many other different places. So let's look at the first 3. For number 1, of course, forms crystals. Ions are different sizes. Much like if we stacked golf balls and tennis balls together, you'd be able to fit a different ratio of golf balls around tennis balls, and vice versa, than you would, let's say, baseballs and basketballs. So because these have different attractive forces, you get a variety of different types of crystals. You've got your simple cubic, much like sodium chloride is. You have a body-centered cubic, so there's something in the middle with other things around it. You have hexagonal, body-simple teragonal, and all these different combinations in which you have these different structures and different orders based upon these different sized ions. So again, we also have the idea that what attracts positives? You're right, negatives do. What do negatives attract? You're right, positives. So if the idea is that any positive can attract as many negatives that can possibly fit, the same would be true with the negatives attracting positives. Much like you think of a magnet attracting paper clips. How many can it attract? As many that can get physically close to that pole to attract all those paper clips. So again, we have these different shapes because all of these can come into contact with each other, in which then they can combine and form into these different structures. Now secondly, high melting points. Take a look. We have the idea of all of these attractions. If this one that I circle in red wants to be freed, it needs to break 1, 2, 3, 4, 5, 6 bonds to actually be freed by itself. And we think of melting, we think of free to flow, free to move around, not locked into place. And that's true with each and every one of these ions. So because each of these ions need to break so many bonds, they need to overcome so many multiple attractions, so much heat is needed in order to give them the energy to overcome those attractions. Now, when we think of the third one, strong attractive forces between ions in 3D, that's a lot like what I was just mentioning with the idea of melting points. Now, if we look at just a couple ideas over here with the melting point, we can see that something like magnesium and oxygen has a huge melting point because of the fact that we have this ion, which is a 2 plus, attracting another ion, which is a 2 minus. So that plays a different role in its attractive forces. So we could see that this one up here at 636 has a weaker bond than something down here at 845. So this would be stronger. Because if we had to heat it up higher, that means it needs to overcome more or stronger bonds. And so if it has to overcome stronger bonds, therefore we need a higher melting point in order to achieve that. So again, it needs to overcome many bonds, which is true in all of these. However, the strength of that bond is kind of illustrated by the melting point at which it needs to occur, because if it's melting, it's overcoming those attractive forces. All right, let's take a look at the next two. When we think of them being brittle, we have to think of all the positives and negatives that are attracted. And how wide is an ion? Well, let's just put it this way. It's not very wide. So if you apply this external force, like hitting it with a hammer, you've now shifted these solids one ion, putting now positives next to positives, negatives next to negatives, and other positives next to negatives. And this would carry on all the way down the crystal. Now again, opposites repel. So these are going to want to push away from each other in all cases 100% of the way down, which makes it very easy to crack. On the other hand, we think of, better adjusted, when we think of number 5, range of dissolving in water. So in something like sodium chloride, which easily dissolves in water, yes, these are strong bonds between these, in all directions, but it also has a very good sized ion in which it's very easy to be able to attract it in water. So water has the ability to pull these apart because it's what's called a polar molecule. If we kind of zoom in to see this here, this negative has these positive areas where the hydrogen is. So that's why they're all pointed this way. On the other hand, when we look at the sodium, you can see that the negative side is pointed towards, not that one so much, but the negative side is pointed towards the sodium. So what that does is that helps hold these apart, holds the positive and the negative apart, because this positive side is attracted to this negative side is attracted to this positive, so that enables to really lock in a buffer between the two so they can't rejoin. And because there's so many more water molecules often than the ionic solid, that can have an overpowering force in order to do so. Now again, that's not always true. If we had something like our lead iodide that we talked about, where did we talk about that? Over in the third slide at the bottom, the PbI2, that one does not dissolve in water because lead and iodine hold such a strong force that the water cannot overcome it. At least not overcome it too much. It technically does dissolve, but a very, very minute amount. We'll be investigating that later in the year. And that would be called insoluble. All right, let's take a look at our last two. Thinking about number 6, large energy release when attractive forces are overcome. Well, let's take a look at this little thing called lattice energy. It's how much energy it takes in order to make these, but also looks at the same idea in the reverse to separate them. Now you see lithium and fluorine has a 1036 kilojoules per mole value. That indicates it's a very strong bond. As we go down and the ions are much weaker, still the same charge, you can see that drops quite a bit. Same holds true as you go down the column for all of these. As you go down, it gets less because of the attractive force of the iodine ion compared to the fluoride ion. This even holds true with 2+ charges. The reason why these are much higher is because now you have twice the charge that is present, and so you're going to have more fluorines compared to the, in this case, beryllium and calcium and magnesium. You also might notice that as you go across and down, it becomes much further because you have now 3-to-1 ratios. So these fluorides make a very strong charge, and when you think of I have 3 more fluorines for every 1 aluminum, number of bonds goes up, strength of bonds goes up, so does the lattice energy. The last part has to do with conductivity, Normally, as a structure, as solid, the charges are not free to move. In order to have electric flow, you need to have charge flow. In a crystal, they can't move. And water doesn't have any charges because molecules, which we'll get to in our next section, are never charged and they're made of atoms. So atoms aren't charged by themselves, and therefore combinations of atoms aren't charged. So that's why it does not conduct electricity. However, when you pair them together, you know that the water separates the charges when it does dissolve, and if ions are free to move, we get electricity and have that flow. So again, they work in combination. The water molecules don't conduct themselves, but they almost act as a vehicle in order to allow those ions to move, therefore conduct electricity.